Okay, angle relationships in circles. Hey, we're going to encounter a bunch of, or a couple different proofs, or not proofs, but theorems in this lesson. And what I would do if I were you, I'd pause and I'd try to draw out the picture of what we're describing through those theorems, and then copy down the formulas, understand how the formulas work. If you're in my class, during your actual assignment, you'll be working through some proofs to show why those theorems work. I'm not going to go through the proofs in this lesson here, okay? But if you really want to know more and more why they work, you can sit down with your teacher and ask them, and you, in my class, you'll go through the proofs and you'll have an opportunity to ask during class as well. Okay, so the first one, tangent and intersected chord theorem. If a tangent and a chord intersect at a point on the circle, so first thing I'm going to do is draw a tangent, okay, and a chord, and we're going to have those intersect at a point. I'm going to actually call that point X. Okay, and I'll actually label this endpoint here as Y, and just so I can reference the chords, I'm going to put another point over here as Z. I'm going to go ahead and label where my tangent and chord intersect two different angle measures, angle 1 and angle 2. Okay, so if the tangent and chord intersect at a point on a circle, then the measure of each angle formed, okay, so angle 1 or angle 2 is half the measure of its intersected arc. Okay, so what does that mean? That means the measure of angle 1 would be equal to 1/2 the measure of the intercepted arc, and then the intercepted arc is xy. Now, like I say, there is a reason why that happens, and it has to do with triangles and exterior angle theorems, different things like that we can get into, but it's something you'll do in your assignment in my class, and something you kind of walk through with your teacher if you wanted to. Okay, do some more research on why it works. Measure of angle 2, you could also do that one. Measure of angle 2 then would be equal to 1/2 the measure of arc. Well, this is big arc, arc xzy. So angle 2 encompasses this entire intercepted arc right there. So arc x, z, and y. All right. So applying that, find the measures of each indicated arc. Assume that the lines which appear tangent are actually tangent. Okay, so let's say I want to find arc FG. Okay, arc FG is right here. And I know that the measure of arc FG is equal to, or 1/2 the measure of arc FG is equal to angle FEG. I didn't give myself a lot of room there. It's FEG there. Okay? And so, excuse me there. I'm just going to rewrite that. That looks like a bunch of gibberish. So I know, based on my formula, the measure of angle F, and it's not FEG, it's EFG. Boy, I was really messing that one up. So EFG, that angle, is equal to 1/2 of the intercepted arc. And the intercepted arc here is FG. All right, I think I have it correct now. There we go. So the measure of angle EFG is actually 76 degrees. And that is equal to 1/2 of its intercepted arc, FG, which we don't know. That's what we're trying to find. So to find the measure of that arc, we'd have to get rid of this 1/2 by multiplying both sides by 2. That ends up giving us 152 degrees is equal to the measure of arc FG. This arc, 152. And this angle is half that intercepted arc. Okay? Let's go ahead and take a look at this next one. Assume that lines that appear tangent are tangent. So we can say that arc S is tangent to the circle, and that QR is a chord here. Okay? We want to find the measure of angle R, or QRS. So we're looking for this angle right here. So we know that the measure of angle QRS is 1/2 of its intercepted arc. And the intercepted arc happens to be arc QR. And we know that our QR is equal to 146, which means the angle QRS is actually equal to half of 146, or 73. Okay, this angle is half of that arc, 73 degrees. Now I went through a bunch of work there. Eventually you're just going to recognize it and put the measure there. Okay. Let's talk about some intersecting lines. The point of intersection for two non-parallel lines that intersect the same circle, and each other for that matter, can occur in three locations. So we sketch each scenario. So I want to draw a picture of where these three different locations would intersect. Okay. So first, my lines could actually intersect on the circle. So I have two non-parallel lines that intersect, and they can intersect on the circle. Okay. And so if I were to call this angle 1, actually yesterday in our lesson we talked about this this angle right here. This angle right here is called an inscribed angle. And if I were to say that this is A and B, some things I know about an inscribed angle. Well, the measure of angle 1 is equal to 1/2 of arc AB. Okay. Well, let's go ahead and draw a different picture here. So we have this picture where our angles are going to intersect inside the circle. Or, excuse me, our non-parallel lines will intersect inside the circle. Okay, and notice I have angle 1 again. It's just kind of moved off the circle to inside the circle. All right. And in this case, measure of angle 1 changes here. It's inside, it's being included, but we're still at a 1/2 relationship. It's just we have to take 1/2 of. We no longer have just arc AB to deal with, because we've created another arc over here by moving it inside. We now have CD to deal with as well. So it's 1/2 of arc AB plus arc CD. One way to think about it is there's this cross makes almost like a plus sign. Okay? So angle 1 is 1/2 of this arc plus this arc. Now once again, there's a big proof for this. Okay? Angle 2, or excuse me, not angle 2, but the next one here, outside of the circle. Okay? So let's say our non-parallel lines intersect outside the circle. Okay? And so angle 1 is now moved outside of the circle. All right. So in this case, since it's being left out, as one of my students said today, Caden actually said that. Well done, Caden. Okay. We know if I were to label this, I still have two arcs I have to deal with. So we'll have CD here this time, and we'll have AB here this time. But since the angle's on the outside, it's being left out, we still have that 1/2 relationship, just like we had here and we had here, but now we have to deal with arc AB, and rather than adding it to CD, we are taking it away. We're taking CD away from arc AB. So we're subtracting. It's on the outside. Okay, those different scenarios help us with these theorems here. If two chords intersect inside a circle, then the measure of each angle, okay, so we're going to have two chords now. They're going to intersect inside the circle. Notice that picture right there is this picture right here. Okay, it's just without the extra ends on it. Okay, when we have that, then the measure of each angle is half the sum of the measures of the arcs intersected by the angle and its vertical angle. So here's angle 1, here's its vertical angle. If we were to say this was A and this was B, there's arc AB. And C and D, here's arc CD. So angle 1 intercepts AB, its vertical angle intercepts CD. So we have measure of angle 1 is equal to 1/2 AB plus CD. And that would be the measure of each of those. All right. All right. Okay. Angles outside of a circle theorem. Well, there's three different scenarios you can deal with when you have an angle outside. You can have a tangent and a secant intersecting. So if I have, say, a tangent line, let's say that that's tangent there, and a secant, and we get an angle formed by it. We'll call this A here, call this B here, and point of intersection here we will call C. Okay, so we have a tangent and a secant. Angle 1, well, based on what we just talked about a minute ago, the measure of angle 1, remember angle 1's being left outside the circle. Okay, so we have 1/2 of the measure of angle BC, or measure of arc BC, not angle BC, minus the measure of arc AC. Okay. So being left out, kind of subtracting it, kind of a nice way to think about it. Caden said that in class, so well done. All right, we could also do two tangents. We're going to have this tangent here and this tangent here. We're going to actually say that they intersect there and there. We're going to label that P. We're going to call this one Q, and we're going to actually, let's put Q over here. Okay, we'll go alphabetical, which means that would be R. Okay, there's angle 1. Actually, let's use angle 2 this time, so we're not using the same angle. So in this case, the measure of angle 2 is going to be equal to 1/2. In this case, we have PQR. The bigger arc always goes first, and we're going to subtract the smaller, PR. Okay. And then we have the last scenario where we have two secants. A lot easier to draw than our tangents. We'll call that one angle 3 this time. Let's label this W. We'll label this X. And then Y and Z. Okay. So measure of angle 3 this time will equal to 1/2. And we're still subtracting arc XY, measure of arc XY minus the measure of arc WZ. Okay. Hey, we didn't even finish the statement. Then the measures of the angle formed is, hopefully you know it now, 1/2 the difference of the measures of the intercepted arc. Okay, so we have a sum situation where the angle's inside. We have a different situation where the angle's outside. Let's go ahead and look at some problems here. Find the value of X. So the first thing you need to ask yourself when you're looking at these is, does it happen inside or outside? Okay, is the angle I'm looking for dealing with inside or outside? So in this case, it's inside. Inside means I'm taking 1/2 of a sum. So my angle, in this case, X, is equal to 1/2 the sum of the intercepted arcs of it and its vertical angle. So 127 plus 97. So it'd be 1/2 of 127 and 97 is 224. And that gives you 112 degrees. So X is 112. Okay, looking at our angle that we're dealing with in this picture, the angle's outside. So when the angle's outside, the angle is going to be equal 1/2 of a difference. We're subtracting in this scenario. And the difference is the big arc minus the small. Well, I know the small is 110. Well, the big is, well, that's 360 minus that 110. 360 in a circle, and then we subtract out the 110 we know. 360 minus 110 is, well, that's 250 degrees. Okay, so this arc they don't label is 250. So X is 1/2 of 250 minus 110, or 1/2 of 140, which x then is 70. All right. Next one, hey, we're dealing with an intersection inside again. Okay. And so that means I'm dealing with an angle where I'm going to be taking half of a sum. It just so happens, though, here are the arcs they give me. Well, that's fine. I can deal with the arcs. Arcs go here, x and 85. Notice my variable's on the inside of the parentheses. However, I need this angle or this angle. They're congruent. Notice that either one of those angles is supplementary with 128. That means this plus 128 has to equal 180, meaning this angle right here, 180 minus 128, is actually 52 degrees there. Okay, so 52. So 52 equals 1/2 x plus 85. Now I'm going to multiply by 2 to get rid of that 1/2, so it's going to give me 104 is equal to x plus 85. Okay. And then I'm going to subtract that 85. X is going to be 19 degrees. All right, this last one over here, we're dealing with an angle on the outside. It means we are taking 1/2 of a difference. The arcs I'm dealing with, our big arc is x, small arc is 65, and then my angle is 44. So it's just figuring out which of the ones you're using and then plugging in the pieces, right? Double that 44 to get 88, that gets rid of that 1/2. Add that 65 over, you end up with 153. All right. Hopefully that makes sense there. Hopefully you're pausing and trying them on your own as well. Let's go ahead and look at our last set of theorems here. Okay, first one here, an angle whose sides, whose sides are tangent to a circle is called a circumscribed angle. So when I have an angle whose sides are tangent, you have what's called a circumscribed angle. Okay, so if I were to say this is W, this is X, where it intersects here, and this is Y. And in fact, let me go ahead and put the center in here best I can. And I'm actually going to draw in 2 radii, and we're going to call that Z. One thing I want to point out here is kind of working with this theorem. Okay, the measure of a circumscribed angle is equal to, well, let's see. Let's say I actually, you know what, rather than drawing this picture up here, you can leave it there if you drew it, but let me go ahead and draw it down here, right, since I have a circle working with the theorem. Oops, that's a bad tangent there. That is as well. We'll eventually get it. Hey, that's much better. Okay. So let me go ahead and draw in what we just had there. All right, we're going to say right there, that is going to be my Y. We'll call that Z. Up here, we will have W. Okay. Now notice, now I realize that that is not much of an angle there, but I do have 1, 2, 3, 4 sides. So I do have a 4-sided figure, a W, X, Y, or WX, ZY. I have a quadrilateral here. WXZY. Note that WXZY has 360 degrees in it. One thing that I know about this quadrilateral are it's actually a kite because this side is congruent to that. That's a theorem we talked about earlier. And this is congruent to that because they're both radii. The other thing I know is that radii intersect tangents at right angles. Meaning this angle and this angle take up 180 degrees of my 360. Meaning angle Z plus angle W have to equal, well, 360 minus 180, 180 degrees. That's what's left for those two. So the measure of a circumscribed angle is equal to 180 degrees minus, so the measure of angle W in this case, so if we were to write that here, angle W, is equal to 180 degrees minus the measure of the central angle, much better than western angle, okay, which in this case is angle Z. That intercepts the same arc, okay, and here's the arc it intercepts. All right, so if I want to find W, I just take 180 and subtract Z. In fact, if I want to find Z, I go 180 minus W. All right, there you got it. Okay. So actually, to write out the formula for the theorem here, this would be measure of angle W is equal to 180 minus measure of angle Z. Okay, very good. Let's go ahead and apply this here. Find the value of X. Well, that should be pretty easy now when you look at it. Here's your intercepted arc. You have your quadrilateral. So measure of angle X, or excuse me, X, not measure of angle X, X is equal to 180 minus 142. All right? So X is 38 degrees. A little more complex over here, and so I'm trying to throw in a little tougher one here. Okay, let's go ahead and take a look at this one. So first thing I look at, notice I have a quadrilateral. If I were to actually draw in that and that, okay, my radii, unbelievable. Turn my tablet here so I can actually, okay, a little better. If I draw in my radii, I know that this angle right here plus this angle here have to add up to 180 degrees. Well, that doesn't help tons because I don't know that angle. All right. Now I could figure that angle out, right? But I want to find angle X. Well, let's find angle MLO first. So measure of angle MLO is equal to 180 minus 40. And 180 minus 40 is, well, 140. So this angle right here is 140 degrees. Now one other thing we know about this, measure of angle MLO is 140 degrees, but measure of angle MLO is also equal to the arc MO, right? The arc is equal to its central angle, okay, or the central angle is equal to the intercepted arc. So I know MO is, well, if MLO is 140, then MO is also 140 by substitution. That means this arc is 140. And how is that helpful? Well, notice, let me go ahead and trace out this angle right here. Notice this angle. This is an inscribed angle. And that inscribed angle right there, that inscribed angle is intercepting our arc MO. So angle N, okay, is equal to, if you remember inscribed angle theorem there, it is equal to 1/2 the measure of its intercepted arc, which is, in this case, 1/2 of arc MO. And arc MO, we know, arc MO is 140. So 1/2 of 140 is angle N, which in this case is 70 degrees. And that just happens to be our value of X. 70 there. All right. Well, I think that's it. Yep, that's all I got for you. Good lucky.